problems, a few technical hitches, but we got there eventually. I'm hoping some people are watching live. If you are watching live, then you do get the chance to ask some questions. Okay, so today, my name's Jason Jordan. Today we are going to be, or I'm going to be discussing and looking at sea level change, both the ups and downs of global sea level change, and then, as I've said, for effect, with a giant wave thrown in. So if you are watching live, then you can send questions or through Menti. So there's the join code there, or you can scan that QR code to the right. Okay, or you can follow that link through. So I'll just leave it there for one moment, just in case anyone wants to follow up on that. This probably will take about 40, 45 minutes, and then we've got time for questions. So just give it one more minute, just in case people want to scan the code. I guess you can pause it in YouTube and scan. Okay, let's move on. So the plan, what was I going to do today? Well, I want to talk about sea level change for a number of reasons, but mainly so that I can try and get through to you how complex this is, a better understanding of what's happening around the world, what's happened in the past, what's happening now, what's happening in the future, and then at some point to start talking about kind of catastrophic problems, mainly because I find them really interesting. And from a geographical perspective, the impact of hazards on us and everyday life, whether it's in the past or indeed in the future, is of great importance. So what we're going to do today is I'm going to try and define what sea level is, which seems like a really obvious thing, but it's not quite so simple. I'm going to look at the causes and the drivers as to what causes that change. And through doing that, we'll start to think about what the consequences are of a rising sea level globally and in the UK. Then we're going to consider what that really means in terms of the future. And I haven't forgot, I will put a big wave in at the end, okay? Just for those that are interested in the big hazards. So first things first then, what is sea level? Well, sea level goes up and down on a daily basis. And for areas that have a perceived normal tidal regime, a semi-diurnal tide, that's two high tides and two low tides across a day. So every 6 hours, it's going from high to low and backwards and forwards. And that's all down to the gravitic pull of that giant ball of gas that's burning at the center of our solar system, our sun, and the moon. More the moon than the sun, because it's closer, even though it's smaller. When the two are in conjunction, we get really high tides and really low tides. They're called spring tides. And when they're at right angles to each other, it's kind of offset, and we have a slightly, not quite so high, but still a high tide, a neap tide, and not quite as deep and low as a spring low. We have a neap low tide. And the picture on the right should demonstrate that for you. We've all been there. We've been to the coast when it's low tide, and we've been to the coast when it's high tide. We know what this means. This isn't sea level, okay? This is daily change. So we need to think about things that are on a longer term, okay? But first things, we do need to consider one more thing, and it's a pet hate of mine. I've just described very briefly what tides are. And the fact that the water comes in and out, it is a wave, and that's called a tidal wave. And one of the things, and I am going to brush up on this at the end when I talk about big waves, is something called a tsunami, okay? So it would seem that a lot of people think these two are intrinsically linked, and they are not at all, okay? So when we describe a massive wave that has been created by a huge amount of water being taken out and displaced from where it normally is via a meteorite impact or an earthquake or something falling into the sea like a landslide, that is a tsunami. When we talk about the gentle rise and fall of the sea across the day, every week, every year, forever, that is a tidal wave. So that is low tide. That is the effect of a tidal wave, okay? This is a tsunami. It's not real. But either way, I think you get the picture. You understand the two differences. So from now on, consider yourself educated. Never make that assumption again. And if anyone does call a tsunami a tidal wave, then you have the right to castigate them and say, no, you're wrong, and tell them why. And if it happens on the news, then write in, make a complaint. But I think we've now got that covered. Anyway, let's move on. Let's go back to our sea level. Is the sea level? So if we take away that tidal impact, if we take away the sun and the moon, which can clearly never happen, we end up with something called an equipotential surface. which is, so if all the water has stopped moving around and we leave it to settle, okay, like a bath that hasn't been stirred around, then we end up with this equipotential surface. And this is an image that's taken from a gravatic satellite called the Jason satellite, actually, not named after me. But either way, it shows you areas of less gravatic anomaly. So they are the redder colours. And it shows area of greater gravatic anomaly, so greater pull, okay, density of the crust. And they are the purple areas. And the measurement of this is in meters. And so we have areas around Iceland of very thin, new crust, which isn't very dense, where we see sea level of around 60 meters above what we would normally have for the equipotential surface, right round to the Indian Ocean and around the Indian subcontinent, where we see measurements there of minus 90 meters. So even if we take away all the gravatic pull of the sun and the moon and all the other movements of the ocean gyres, we end up with a sea surface that isn't level anyway. That's quite a conundrum. This next image actually shows you it with the numbers on, and the little stippling that you see are the negative areas, and the clear areas are the positive areas. And this was first devised in the 1970s and worked out mathematically by Nicholas Morner, and has been used by many. And it wasn't until the launch of the Jason satellites that this could really be checked, and it's found to be exactly right. Okay, so we have this plus 60 around Iceland, this minus 90 around the Indian subcontinent. The very notion that sea level isn't level is kind of baffling, but we need to park that idea. What we now need to do is try to figure out, if the equipotential surface exists and there's gravatic pull and there's also tides, what actually adds ocean volume? Because if we add water to this, no matter whether it's high or low, it's going to go up at the similar sort of rate. Well, we would expect it to. So what can cause sea level to rise and fall? So one of those is things called this thermosteric effect. So the physical warming of a body will mean it expands, and water does that. The H2O, the space between the atoms starts to move apart as it starts to get warm. It expands, it takes up more space. So the thermosteric effect of the oceans is that when you start to warm the atmosphere above, it warms the surface of the oceans and they physically expand. And this is one of the drivers at the moment with global sea level change, because of anthropogenic climate change and the amount of CO2 we're putting in the atmosphere and global warming. The oceans are physically getting bigger. Time scale for this, it can be yearly to decade to century. So quite short time scale. Magnitude, not a lot, probably between 1 and a maximum of 10 meters globally. So this is a really interesting dynamic effect, but it's not very big and impressive. Okay, so we're going to park that. We're going to forget about that one for now. Next one would be what on the longer term, we can physically open and close ocean basins. We can change the shape of the Earth, which is amazing to think we can do that. Well, we can't, the Earth can itself. But we're talking about plate tectonics, okay? Very long-term drivers, hundreds to thousands of millions of years. And a really good example of this would be the Wilson cycle. So I'll quickly guide you through the Wilson cycle. We go from what we term an embryonic stage, where the plates they've come together and they've started to lift up and move apart into what we'd call a rift valley. So the East African Rift Valley, that's stage 1. As they start to lift and move apart, they pull apart even more, and you have down thrusting and water will flow in. So that's juvenile stage B. And the Red Sea is a good indication of that, a very young proto-ocean. As it starts to pull apart, at some point it will have a mid-ocean ridge, which will start to actually expel magma and will push itself apart. And that would be a mature stage, stage C in this particular image, and that'd be the Atlantic Ocean. It's a good example. We then start to see that decline as we get subduction at its edges, so the Pacific Ocean. And then eventually the ocean, as it starts to subduct, it will get smaller and smaller into its terminal stage, very much like the Mediterranean Sea today. And eventually the sea will disappear completely, and we'll have orogenic mountain building, where two plates come together and they push each other up into mountains, for example, the Himalayas. Over time, the Himalayas will lose energy, they will erode down, and then they'll start to pull apart, and we start the cycle again. We don't need to concern ourselves with this in terms of sea level change. It just takes too long. Here's another scenario, how we can change sea level, but it's crazy. It's never going to work. We could take all of the fresh water that exists on the planet, from the lakes, from the aquifers, from the rivers, and empty it all into the ocean. We can't do that because that means hydrological cycle has stopped. It's never going to stop. We can speed it up and slow it down, but we can't stop it. So it's an impossible scenario. But if we did take all of that fresh water, it would only add about 10 meters maximum of sea level rise. So it's an impossible scenario, and it's not adding a huge amount. So we're only really left with one thing that works on both short-term timescales into the medium-term geological and is of a magnitude large enough to be of great interest. And that's ice. We can make ice form on the planet when we go into a cold period, and it takes water out of the hydrological cycle and it stores it in huge ice sheets on the land. And as soon as it does that, it's removing water from the ocean basins. And the last time this happened, we had a large ice age, which ended around about 24 to 25,000 years ago. And oceans across the world were 120 meters lower. Now, when that ice builds up on the land, it pushes the land down. We'll get to that in a minute. But either way, when it starts to warm up, when the atmosphere warms up and the ice starts to melt, it returns the water to the ocean basins. And as it does that, the sea levels start to rise. And lo and behold, when all of that ice is melted, they rise up to their highest point. So we're now talking about a process that operates over the 100 to 1,000 to 10,000 years, so fairly short time scale, but is so big in magnitude. We're talking about 100 to 120 meters of sea level rise and fall, which means our current coastline, if we were going to go to an ice age, would actually be where the edge of the continental shelf is. It would look very different, the globe. So accretion and wastage has an effect on both the sea, okay, the water in the ocean basins going up and down, but it also affects the land, okay? Because if we're talking about removing enough water from the ocean basins to make it fall by 120 meters, we're talking about kilometers of thickness of ice on the land, and that will push the land down. So what we end up now, it's all about balance. So on the left-hand side, we have changes in the sea, and we've talked about these already, these kind of big tectonic changes, or these geoidal changes, the gravatic pull of various bits, the dynamic sea surface, which is part of that thermospheric effect, and then the glacial part. And we refer to changes in the ocean basin as eustasy, changes in ocean volume and ocean amount, eustatic, eustasy. But we also have changes on the other side, which are about the land moving up and down as well. These are referred to as isostasy. And we can have tectonic isostasy. We can have a deformation of the land masses through the Wilson cycle. So it's geoidal deformation. We can load the land with sediment, like we would a triple plate boundary or maybe a delta. So we can have sediment compaction. But once again, the key bit in here is isostasy linked to glacial ice. So glacial eustasy and glacial isostasy. They are the key things that we need to consider for interpreting our past, our present, and our future sea level. So let's think a little bit about glacial isostasy. What's it all about? Well, effectively, we have the crust, the lithosphere, the hard rock, floating on top of the asthenosphere, or the mantle. When in a mountain range, it starts to get colder. When we move into an ice age, the mountains get colder than the lowlands, and the ice starts to form, and eventually it coalesces into a large ice sheet, or eventually a large ice cap if it gets big enough, and it will push the land down. It will push it into the asthenosphere. So we have depression. As we push the land down, elsewhere, it will be pushed up. So at the periphery of an ice mass, the land actually rises up during an ice age, but at the center of the ice mass, it gets down thrust. When the ice melts, the land pops back out of the asthenosphere like a cork bobbing up in the water, but then the peripheral areas will down thrust. So this is really complex, but in itself, it will produce landforms. So here we have an absolutely classic landform from Scotland. This is from the Isle of Islay, famous for its single molts. The Isle of Islay has these incredible flat terraces that are 10, 15, 20 meters higher than modern sea level. These are old beaches. These are old terraces. These are raised platforms. And they are not an indication that sea level has ever been higher, because it hasn't really in this area. What's happened is the land has been lower. The land has isostatically lifted up. So this is a bit of an issue when we're trying to think about recreating past sea levels, because we now realise the land isn't static. The land is moving up and down. And in the last ice age, which we'll get to in a minute, but in the last ice age, there was a lot of ice formed over Scotland and northern Britain. But there was very little in southern Britain, okay? And because there was very little in southern Britain, it almost acted like this peripheral area. So in one area in the last ice age, the land was pushed down and another area was lifted up, and vice versa, now it's melted. So we have land uplift in Scotland, but in London, for example, we now feel, in the south of Britain, we now feel land submergence. It doesn't matter what sea level's doing, the land is physically falling, it's subsiding, and in other areas uplifting. And we'll come back to that in a bit. So one of the key things is not just about the land, it's about all that ice. It's about that water being taken out of the ocean basins and being put on the land. So we could have a graph, we could have a line graph of what actually happened that tells us a huge amount about the ice ages. So this particular graph is the global picture. This is a eustatic graph. It doesn't actually really apply to anywhere. It's what's happening in terms of the ocean volume in the ocean basins. So across the bottom on the x-axis, we have thousands of years before present, or thousands of years ago, 24,000 on the left-hand side, right up to the present, 0 on the right-hand side. On the right-hand scale, or the y-axis, we have meters of sea level change with 0 or present mean sea level at the top. And these are all negative numbers, down to about minus 140 on the scale. So the key thing we see here is if we chart back in time on the left-hand side, we see the last glacial maximum, which is on the graph, it's noted on the graph, around about 24 to 22,000 years. The air started to warm up, we started to come out of an ice age, the water started to return to the ocean basins, and the ice caps started to melt, and we see sea levels start to rise up to around about 15,000 years ago. At that point, there was a sudden jump in sea level, global sudden jump, okay? We'll get back to that in a minute. Then it leveled off again, then it jumped again, and it leveled off again, then it jumped again, and then at about 6,000 years ago, it kind of leveled out, okay? So one of the things that I want to draw your eye to at this particular point is what that first big jump about 15,000 years ago. It's noted on here as being Meltwater Pulse 1A. Very interesting, Meltwater Pulse 1A. So Meltwater Pulse 1A describes the melting and draining of a proglacial lake, a lake at the edge of a massive glacier, okay? In particular, it's thought that this event is to do with a large ice sheet that sat over North America that's no longer there. I'll show you it in a minute. But basically, the amount of water that entered the global system created this big jump in sea level change, a huge jump, okay? Over just a space of 500 to 1,000 years, it jumped about 20 meters, which is astronomical compared to what sea level is doing today. Look where we are today, and over 6,000 years, it's changed by about 2 or 3 meters. So we're talking 20 meters in about 500 years, okay? A massive jump. So here we have a picture of North America, okay? So it's quite tricky to figure out where North America is there because it's covered by this massive ice sheet called the Laurentide ice sheet. And there's another ice sheet to the left, to the west. This is the Cordilleran, but this is in a stage of decay. The two used to join up at one point. But here we have this massive ice sheet, the Laurentide ice sheet, and sitting behind it to the west, we have two lakes, two glacial lakes, Glacial Lake Agassiz, noted on the map in the middle, and below it, Glacial Lake Ojibwe, okay? These glacial lakes couldn't drain. They couldn't drain into the sea. They were sat inland of the ice sheet. As the ice started to melt, they started to fill up, and eventually at some points they either lifted the ice sheet and drained through into the north part of the Atlantic, or it's thought they could have drained through the Mackenzie River to the north or the St. Lawrence to the south. Either way, these big pulses of meltwater entered the North Atlantic Ocean and they changed global sea level dramatically. Okay, so there's some calculations there, very basic calculations. Sea level rise rates of around 47 millimeters a year during meltwater pulse 1A. 47 millimeters a year. Doesn't sound a lot, it's half a centimeter a year. Currently, sea levels are rising at 3.6 millimeters. So it's more than an order of magnitude more. There's another period that we'll come to later called the early Holocene sea level rise, meltwater pulse 1C. And we'll discuss the implications for that later and possible implications for the future. Either way, this is our past. This is our past, this rapid rate of sea level rise caused by meltwater pulses, this slowing down, rapid rate again, slowing down, rapid rate again. And then at some point, we physically ran out of ice to melt. There is no longer a big ice sheet sat over North America. The Laurentide has now gone. The Cordilleran has gone. The British-Irish ice sheet has gone. The Fennoscandian ice sheet has gone. So at 6,000 years ago, we just tail off and we enter this modern period of sea level change. So this graph here shows you the sea level change from the 1970s through to around about 2010. And the important thing about this graph is that it covers a period that once was the future. Okay, so this is an output of the Intergovernmental Panel on Climate Change and their various reports every 4 to 5 years, coupled with, because we can now look back over that period, the real instrumental data. And the key to take from this is that from about 1990, there was a series of reports with a series of predictions about what sea level might do because of global warming, series of scenarios, business as usual scenario, best case scenario, you know, we stop producing CO2, there is no global warming, to the crazy scenario that we double the amount of CO2. So the worst case scenario is the line that moves across the top. An input over this is the tide gauge record of what actually has now happened over those periods of climate change scenario estimates from the past. And we do chart along the worst line, okay? So this is the new scenarios for the future. These scenarios here are driven from 1990s on the left-hand side right through to the end of the century, 2100. And the key bits here, there's a series of different scenarios that are embedded. The best case scenario is the lowest and the worst case is the highest. And inset in here is a graph that shows you that previous one with tide gauge and satellite observations mapping across the worst case scenario. So the thing to take from this, what is our future? What is the future got to hold? Well, the current rate of sea level rise is 3.6 millimeters a year. That's a eustatic rise. That does not take into account isostatic effect, okay? It does not take into account land movement. But as you can see, it's not a straight line increase, it's somewhat exponential. So we are expecting rate rise to occur soon. We are in 2021, and we are expecting to start to see that rate to start to increase. And in fact, there's some modern research that's come out, some research that came out just this year, which is suggesting that we're closer to 4.1 millimeters from various different tide gauge records. Either way, we are going to start to see a rate rise increase. Now, think back to what's happening on the post-glacial sea level rise. At 6,000, it just tails off. So we're still only talking about small amounts. But we see a maximum on here of about, by the close of the century, 0.8 meters, so 800 millimeters, okay, by the close of the century. And it's argued by many that the Intergovernmental Panel on Climate Change scenarios and their driving of sea level is on the lower side. Even though that's the worst case scenario, we are mapping across the worst case scenario. And some have argued it could be 1, 2, or 3 meters as opposed to 80 centimeters. Either way, this isn't necessarily what's going to happen in Britain. And it's not going to happen in Britain because of this. On the left-hand side, we see a series of numbers and black circles or white circles. This is some work that was produced back in 2002 by two researchers that were in Durham, Ian Shannon and Ben Horton. And the black circle, this is an amalgamation of all of the different sea level records from around the UK. It's been updated a number of times, but this one illustrates it very well. This shows you either for the circles that are white with a negative number next to it, or the circles that are black with a positive number. These are millimeters per year of land movement relative to sea level. What this shows you is Scotland is still isostatically uplifting, it's rebounding. We have areas around Rannoch Moor, for example, that are between 2 and 1.6 millimeters a year lifting out of the sea. So if we input on that the 3.6 millimeters a year of sea level rise globally, there it's not rising anywhere near that fast because we've got to take 2 millimeters off. But in the south of England, certainly down on the south coast, Marazion Marsh area of Cornwall, we see the minus 1.1, or London, we see minus 0.7 millimeters. So these areas are subsiding, which means any global sea level rise number is exacerbated, it's added to. So the graph on the right-hand side, or the map on the right-hand side, shows you that in terms of relative sea level. This is a little bit out of date now. So you could add some numbers to these, but it shows you that in the south of Britain, over the same time period, we would accept sea level rise of maybe 50 to 55 centimetres, but for northern Scotland, only 25 to 30. This is the remnants of that large ice sheet that once sat over the UK. This is the balance between eustasy and isostasy. And this occurs everywhere in the Northern Hemisphere, everywhere where there was once an ice cap. Very interesting, very complex. So we've got to that point. I did promise a big wave, okay? So we're also going to try and incorporate, or I'm going to try and incorporate into this story a bit of tsunami information as well, because the two actually are intrinsically linked in a fairly worrying way, okay? So a number of years ago now, there was some researchers that were digging around in peat bogs in the Forth Valley, for example, or over on the east coast of Scotland around Montrose. And they discovered in these beautiful areas, these low-lying areas and areas at the coast, they discovered sections within the peat where they had bodies of sand. Not particularly extensive, but layers of sand. It's highlighted on the left-hand side, it says tsunami sand in between two layers of peat. And on the right-hand side, this is actually from Sullom Voe in Shetland. You can see a thin banded layer at the base of this peat section. So there's these layers that were once found. And initially, they weren't recognized as being sand from a tsunami. They were recognized as being storm deposits. But so the story goes, at the same time, people were starting to notice in the bathymetry off the coast of Norway, large section that was missing from the bathymetry, okay? So they were noticing bites that were taken out of the coastline almost in the continental shelf. And remember what I said earlier, the continental shelf represents our old coast. So the period between the continental shelf and the modern coastline is this area that has been transgressed by this rising sea level. And because of the oil pipelines and the oil networks that were being put in, people started to look, and they found near an area called Storegga. They found this area where they noted a large amount of sediment had slid under the sea, okay, so a submarine landslide. So underneath the ocean, not from the land into the sea, but underneath the sea, a large area around this area called Storegga where the sediment had moved down. And when people started to date it, radiocarbon date it, to find out more about when it happened, they then realized that it corresponded with these layers of sand that you found in Scotland. So we start to find that we have a story. And we find that here we have the area highlighted for the slide sediment. It is massive. And we also see across, and it goes from, there's some sites on the northwest coast of Iceland, but also sites on the Faroe Islands, Shetland, and all the way northeastern Scotland, and then across the coast of Norway, these little red dots. These are sites where people have found very similar deposits, which have a very similar date to the sediments associated with the slide In other words, there is evidence for this submarine slide which caused a mega tsunami, because we also find evidence right across the Atlantic. So this map here shows the sites from Scotland, and it has on it what we term the run-up. Okay, so the run-up for the tsunami waves across most of the coast of Scotland was upwards of 5 or 6 meters, up to 10, 11, and 12 meters. These are massive waves. Okay, in Shetland, the run-ups are up to 32 to 33 meters. So when this submarine landslide happened, it generated an absolutely massive tsunami wave. So you're probably thinking at this point, why is this of any relation to sea level? Well, it also corresponds to this. So 10,000 years ago, we weren't a separate island. We were physically part of Europe, connected through an area that's referred to as Doggerland. This was an area of where people lived, where animals roamed, where trees grew, okay, because of lower sea level, because of the preceding ice age. By 7,000 BP, 7,000 years ago, we were an island. The sea had come in through the northern part of the North Sea and flooded the channel. The actual point that it was flooded, the actual point falls into line with a very similar timescale to the Storegga slide tsunami. Whether the tsunami made us an island or not is of much conjecture, and it doesn't really matter because sea level was rising anyway. Remember what was happening in terms of global sea level rise. It was rising up. But this is where the story gets even more interesting. At the point when we move into this early Holocene sea level rise, the Holocene is the last 10,000 years. We're talking now about 8.2 thousand years ago. It's when the Storegga slide happened. It's when we became an island nation. All kinds of interesting things happened around the globe. But effectively, on the Holocene sea level graph, we notice a rate rise increase. We go to about 20 millimeters plus a year, instead of what we are now, 3.6. And it actually corresponds to a meltwater pulse 1c. So in other words, we seem to have a meltwater pulse from the last remnants and decay of an ice sheet, a sudden jump in sea level, and a tsunami. So it's either really bad luck, it's bad timing, or they're linked. So the image here is taken from a paper that came out a fair few years ago by myself and a few other researchers who have been thinking about this for quite a long time now. And we started to put evidence together, and we think, and it's maintaining momentum, it's gaining momentum. We think that the rise of the sea level put pressure on the continental shelf as it rose across it, increased weight, and it reactivated the neotectonics. It reactivated the fault systems, because the Storegga slide was more than likely caused by an earthquake. But we think the earthquake was potentially exacerbated or re-energized because of the loading of sea level. So just think for 1 minute what that means. Earthquakes and volcanoes. What leads to an earthquake and a volcano? They're things that happen deep in the earth. We're arguing that might not necessarily be the case. We're arguing that the rise in sea level, because it was so rapid, that it caused such an increase in weight on the continental shelf. And remember, the land can go up and down because of the ice. So why can't it do it with the water as well? So as it rose across this continental shelf, it reactivated old faults. It caused an earthquake, which caused the sediments to slide, which caused the tsunami. So here we have a map of the Atlantic, both eastern and western seaboards, which show the amount of areas that have had submarine slides. And it is really extensive. There's been lots of submarine slides. So my question to you is, there are lots of areas that have still not yet moved. There are still areas that have lots of sediment, because all of that sediment was in place by the last ice sheet, okay, or by the time period in the last ice age. So we have lots of evidence for slides, but we have lots of evidence where there are still sediments that could slide. So is there a future risk? Well, here we have that sea level rise graph again. It's been flipped around, and it now goes from the past on the left to the present on the left to the past on the right. And we see marked, there's various colours on here. And when you look at the slides later, you'll be able to see a bit of the detail. But I would argue there's nothing to worry about, because we get to 6,000 years ago and there's not a great deal of sea level rise, is there? There aren't these big jumps. There aren't these meltwater pulses, 1A, 1B and 1C. The current rate of sea level rise is only 3.6 millimetres. You know, rates during that early Holocene sea level rise period were around 20 millimetres. And back on meltwater pulse 1A, there were 40 millimetres. There's no way we could reactivate some of these sediments now. We don't have a driver, do we? We don't have a large ice sheet that could possibly melt rapidly and add a meltwater pulse. You know, we've had these 3 major meltwater pulses. We don't have the driver anymore. Or do we? This is a fabulous graphic. Get yourself on the website, show your stripes. This basically gives you temperature over time compared to the average, from the past on the left to the present on the right. What it shows you here is basically we've got a cold past and a warm present. This is global warming since Industrial Revolution. This is global temperature change. You can download it for all different parts of the globe, including the UK. But what we see here is that we are definitely in a warming episode. Global warming is a thing. Climate change is a thing. As we warm the globe, we are going to warm the atmosphere, and as we warm the atmosphere, we warm the ocean, so they thermosterically get bigger. Remember that right at the start. But they also warm and melt land-based ice. We no longer have that big ice sheet sat over North America, but we do have one sat next to it. This is a map of Greenland. And this map of Greenland, it has some interesting things, because this is a basal map of Greenland. This is not the surface. This was produced a few years back now, but it shows you the areas that we think have and are thawing at the base of the Greenland ice sheet. Bearing in mind, it is upwards of a few kilometres in thickness. We have areas that we are pretty sure are still frozen, and areas of uncertainty. And that's because it's the areas in between the thaw and the frozen. The key bit here is, if Greenland starts to melt, which it is, and it starts to add water into the ocean basins, which it is, it's accounted for within all of those sea level rise scenarios. What isn't accounted for is a meltwater pulse, is a catastrophic collapse. And what people are finding now, as they look more at the base of the Greenland ice sheet, as they look more at West Antarctica and the glaciers over West Antarctica and the ice sheets in West Antarctica, and indeed East Antarctica, as they start to look at a quarter of the land surface which is covered by permafrost, all of these areas are melting, some of them more rapidly than others. But as we look at the base of these big ice sheets, we're starting to find more and more evidence of lakes. They're not proglacial at the edge, but they are basal lakes. They are vast areas of water that are not connected to the ocean. So I've called it a smoking gun. I've called it this idea that we know what we're doing. We're warming the atmosphere and we're melting the ice. But what we're less sure about is, are we leading to another meltwater pulse? If we lead to another meltwater pulse, we're going to see a sudden, instead of a nice rise like that, a sudden jump. We're going to see a massive increase in rate. We're potentially going to activate more and more of the sediments that sit on the continental shelf and expose the whole of the Atlantic, for example, to another mega tsunami. But that's just my ideas. So, on that happy note, it is time to end. I hope you found this informative. It's been a whistle-stop tour of both sea level change and climate change, but now it really is time for questions. Thank you.
Thank you very much, Jason. Well, that was a slightly unorthodox start, so thank you very much for
going there eventually.
Yeah, we did. So, yeah, sorry to everyone, but yeah, we were a bit late starting, and thank you to those that have managed to find this link. I will obviously be sending it around, the updated link, so everyone can kind of watch it at a later stage. But no, thank you very much, Jason. That was fantastic.
Pleasure.
So, a couple of questions then.
Okay.
Yeah. So at the start, obviously, you mentioned the Wilson cycle and the closing of the Mediterranean.
Yep.
So if that were to close, what's the process going to happen there then, kind of going forward?
Well, I mean, it is going to happen that the whole of the basin is eventually going to close up, and we're going to find the northern African continent, and Asia is going to slam into part of the European continent, and we end up with a proto mountain building area to rival the Himalayas. But it's quite a long way off. But eventually, yes, we would see all of those land masses would be pushed up into the air. In the same way that there's a band that goes across Mount Everest called the Yellow Band, which is a band of limestone that was laying down under a tropical ocean, the ocean that used to separate Asia from the Indian subcontinent. So exactly the same will happen. That ocean basin will close up and we will end up with a mountain range. The mountain range will grow over time and potentially be bigger than the Himalayas. But that's quite a long way away. So the Mediterranean is very interesting because it's also had periods in the past where it's completely dried out because there is a lip that goes between North Africa and Gibraltar. And guess what? Around about 8.2 thousand years ago, there were mass influxes of water from the Black Sea into the Mediterranean, once again at this same time period. It's all quite unusual. But before that, the whole of the Mediterranean did dry up. And the Mediterranean actually has vast layers of salt at the bottom from when the ocean evaporated. And then when the water did cascade back in, it came as one big waterfall from the Atlantic back into the Mediterranean. Fairly catastrophic event, but it's a long time ago. But yeah, eventually it would go. We would end up with a new mountain range.
Thank you. Well, that leads on quite nicely to and it actually links to something that Michelle Farrell talked about a few weeks ago. When you were talking about Meltwater Pulse 1A.
Yeah.
And she talked about the impact on thermohaline. Do you want to?
So I did consider doing this. And I thought, well, I've already taken 40 minutes and I thought this could go another hour and 40. So Meltwater Pulse 1B was actually the link to it. When that fresh water enters the northern Atlantic, it doesn't just raise global sea levels, it dilutes the brine. As you dilute the brine, it stops those cold, dense waters sinking, which then return and then upwell at the mid-Atlantic around the equatorial band, which then warm up and expand and flow back north and give us the Gulf Stream. So at Meltwater Pulse 1B, we think it actually turned off this thermohalon circulation. And we did have that classic scenario as outlined in the documentary, The Day After Tomorrow. Albeit it didn't actually happen in about 2 days. It happened, but it did happen quickly. It may have happened in about 30 to 35 years. We went from having a fairly warm environment, not quite as warm as today, into an ice age. And that ice age lasted about 1,000 to 2,000 years. And then it all rectified itself and we came back out of it. So there are a number of people think that particular period of cooling in our past was caused by volcanic activity. But as I've already highlighted, increases in sea level, especially these big jumps and these meltwater pulses, reactivate tectonic faults. And there is evidence, quite a bit of evidence, for increased volcanic activity that corresponds with meltwater pulses. The problem you have is, does one cause the other? We're unsure. But either way, Meltwater Pulse 1B and this period called the Younger Dryas, it really was a switching off of thermohalon circulation. So I haven't mentioned that, but if we did have Greenland catastrophically melt, we could potentially have a tsunami. Actually, we could have an ice age. It's a double whammy, an ice age and a tsunami. Thanks for that, Craig. That's a bright note.
As if I knew what to push you on there in terms of questions. No, so I suppose actually I'm going to link it back to the degree, because obviously Michelle talks about this in her video a couple of weeks ago, in her webinar. Adrian touched on the kind of more the future side of things about a month ago now.
Yeah.
Where do you bring this into the teaching? Is it what do you bring in terms of the teaching on the geography degrees?
Well, me personally, I try to bring it into every single thing I do because I'm totally obsessed. I've even got a T-shirt with a mammoth on, but it's faded. I am kind of obsessed by ice ages, and it's because from the nature of what I studied at Coventry myself, so I've come all the way through that system, and I was exposed to bits of information that sparked things in my mind that made me think, I want to do that. And the thing that I wanted to do was try and find out why we didn't know everything. Well, I've been doing this a while and I still don't know everything, and I don't think I ever will, because the more you find out, the more it exposes other areas. But the thing that I loved was how the Earth could go in and out of these ice ages, and how, when you think about all of humanity, we pretty much, as modern civilized, and we go back to ancient Egypt, we all fit into a little tiny bit after the last ice age. And it just amazes me that the way we've adapted. And then we learn, as you do at geography. In fact, my daughter, who's only 10, has learned a little bit about climate change and about global warming. And I immediately go, oh, that's geography. Well, it's not. It's physics, it's geography, it's economics, it's all kinds of things. But within our degree at Coventry, we try to introduce an understanding of all of this as quick as we can. But you can't have all the details. So in the first year, it's about learning how sea level could work. It's about learning about plate tectonics. It's about learning about the basics of climate change. Then when you get into the second year, you start to go in a bit more detail, and you can start to separate them out. So I deliver with some excellent colleagues who are also doing talks or done talks, including yourself, Craig, on rivers and coasts. So all things watery. And we try not to touch on things that aren't watery because they're covered by other people. So the hazard side are covered by Matt, for example, who's done one on hazards already. But you can't help but creep into that area. Climate change, it's led by Michelle, and I used to teach on that module. I don't anymore. I've left her to it because I bring her into my final year module with Adrian, where we get really down to the nitty and gritty about the quaternary. Of course, not everyone wants to do that. Some people want to learn about rivers and modern flooding and sustainable cities and drainage and stuff like that. But I'm obsessed by mammoths. So I will turn everything into that ice age. But for me, we look at it at all levels. It's just the depth that we start to explore. And I know that in certain A-level curriculum, there is Eustacy and isostasy and sea level change. And that's a hard ask to try and cover, because it could be what we term a module, so an entire course of study across a whole semester we could do on that. And that's just one small part of an A-level curriculum. So one of the things I would say is, if you are out there doing your A-levels now, and you think this is good stuff, then doing a degree in geography, and certainly at Coventry, you're going to go into such detail and depth that you're really going to explore how these things are all linked. And that's the key thing. It's the key thing I wanted to try and do today, is try and make some of these linkages, but it is complex. A bit of a whistle-stop tour today.
It is, but it just, again, and I've thought this in all the ones I've kind of hosted, it just shows all the links that we have between all of that. Everything hangs together in my mind through climate change, both historical and future.
Yep. Totally.
Yeah. And it's what we try and embed throughout the whole degree, really.
Yep.
Right. So I've got a few. You mentioned the quaternary. Then
yes.
What's the quaternary? So
the quaternary is the last 2.6 million years of Earth history. And it's effectively the fourth age. So there was the preceding to the quaternary was the tertiary, the third age. Okay, so we are in the fourth age, and it's the last 2.6 million years which are dominated by the flip backwards and forwards in and out of ice ages. So we're actually in the last 2.6, last 5 million years, we're on a cooling trajectory. Temperatures are increasingly getting lower. But what they're doing is they are going up and down, they're oscillating. And the oscillations are getting very big. The oscillations are going to their warmest and their coldest, but the average is getting colder, which is why it's really interesting, because all you hear about at the moment is global warming and the future being warm, which is completely accurate, but we are genuinely in uncharted territory. There is not a point we can compare to the modern levels of carbon dioxide in the atmosphere and the modern temperatures. There isn't a period we can compare in our Earth history throughout the quaternary. We are genuinely in unusual times. And we've got this really weird species on the planet that appears to be changing the global climate, and that's us. So we actually live at the end of the quaternary in a period called the Holocene, the wholly recent period, the last 10,000 years. And a whole bunch of scientists out there are arguing that actually we live in a new period that we're going to call the Anthropocene. So anthropogenic is about people. The problem with geology is It's not a problem. But in order to make the distinction between the past and the present of a particular point in time, it has to be measured in the rocks, in the geology, everywhere. Yep. So you have to have a marker period. So if you think, what makes this period so special about people? You know, you say, well, is it when we first appeared? Because as bipedal apes, that would be 5 million years ago, preceding the Quaternary. Is it Homo sapiens? Well, it's probably when we started to change the climate. But if you go into my garden and dig into the ground, there's very little evidence of the climate actually changing. What there is evidence of is radioisotopes. So, for example, cesium-137 produced through atmospheric bomb testing or nuclear accidents. So what we could do is we could look in the geology for the presence, the occurrence of cesium-137, and it's at about 1940. That could be the start of the Anthropocene. Or it could be our use of microplastics, which now appear everywhere. Where do they appear? That could be the start of the Anthropocene. Either way, the things that we look for those markers are not things to be particularly proud of, I don't think. But yeah, the Quaternary is this big chunk of our past, including our present, and then it subdivides into smaller epochs, the Holocene, and a lot of people are putting forward this notion of the Anthropocene.
Thank you. Yeah, that was one of my next questions. Has the Holocene ended? Because I know it's a nice contentious discussion. Yeah. So my final bit then, and I'll let you go and enjoy the hot weather.
Yeah,
I've been stuck under lovely cirrus all day, so I had no sun at all. So both you and I know that when we're trying to supervise dissertations, the thing that students love are either climate change or hazards that are going to kill people. Let's be brutally honest. Those are the things that people want to study. Yep. So, you talked about Storegga. What's the tsunami risk then to the UK?
Do you know what? It's a really interesting one because it's close to zero. It's very close to zero. We don't live near an active plate boundary. When it comes to actual tsunamis impacting the UK coast, the nearest to us in time, big impact would have been Lisbon earthquake. Is it 1755? Oh, I'm putting it out there.
I thought 66.
Was it? Well, it's around 17.
It's around that period.
Yeah. So the Lisbon earthquake created a wave that did come around, washed around, propagated across and up the Severn estuary. It didn't do a lot of damage, but it did wash across the Scilly Isles. But at the same time, it wasn't catastrophic. But because of that, there is tsunami protection in the naval dockyards on the south coast of Britain. We do have tsunami protection across Dungeness Power Station. So actually, there is a tsunami threat for the active plate boundaries around the coast of Portugal. In terms of tsunami protection for mega slides, no. Because whenever we engineer anything, we engineer for normally like 1 in 100, 1 in 200 year events, maybe maximum if we're thinking of protecting a power station, 1 in 1,000, but it's so expensive to engineer. Storegga happened 8,000 years ago. So we're talking about the 1 in 10,000. And not much beyond that, we start to talk about meteorite impact. So we'd only ever build underground. I mean, we just can't do it. So what are the chances of it happening again? Close to zero. However, it isn't zero. It's close to zero. So with all of the sediments that are there on the continental shelf in areas that are prone to previous slides, a good project would be trying to get hold of the data that you could find on occurrence of sediments that are not necessarily ready to go, but haven't slid. So everywhere where there's been a slide, there must have been bathymetric data and measurements of the sediments that are there. Okay. Then looking at what was the causation of the slide. When did the slide occur? Because some of those slides are just very slow slides and they're not going to create anything. It's the rapid slides that you want. So you want things that have big trigger mechanisms, and it's normally earthquake related. The thing then to think is, well, what triggered the earthquake? And that's the thing where I think from a hazards point of view, a lot of people are going, no, you can't do that. But that's what we've done. We've started to look at what triggers earthquakes, on what reactivates faults. And it's, we think, because of an isostatic component, it's because of a loading component. And it nicely matches up with a meltwater pulse because it's a rapid raise in sea level. A more slower rise in sea level is probably not going to activate faults in the same way, so probably isn't going to trigger it. So what I'm trying to say is mapping of the areas that exist today, coupled with a projection forward into the catastrophic melting of an ice sheet like Greenland, there's your project. Likelihood of it happening, very low. Impact of it happening, very high. Another one with the classic Canary Islands, La Palma, which is Bill Maguire wrote about that and had a number of programs on TV about it a number of years ago. We've got an island there that is, according to Bill Maguire, about to split in half. And when that does split in half through volcanic eruption, half the island will tumble into the sea and will create this massive landslide into the sea and create a massive wave. And it may actually have happened in the past, because we do find tsunami deposits and boulder deposits in the West Indies that are 20 to 30 meters higher than elsewhere. So these things don't happen often, but when they do, they are catastrophic, or could be catastrophic to our modern infrastructure. So from a student perspective, don't expect to be finding it's going to happen tomorrow, but why not look at it? Why not look at the potential for it? Definitely.
Perfect. Thank you very much, Jason. So I think we can end it there. Thank you. Again, ever so sorry for the slight disruption to both you and to everyone watching at the start. If anyone is hanging on at this point, I will send an email out. But please feel free to, if teachers want to be added onto the mailing list, please get in touch. My email is just craig.lashford@coventry.ac.uk. If anyone wants to contact you, Jason, what's your email? It
was right at the start. So I hope no one gets any kind of photosensitive stuff. Hang on. Bear with. Ah, there we go. Cool. So jason.jordan@coventry.ac.uk.
Yeah. So yeah. Go on. No, over to you, Jason. Go on.
No, I could say, so if you have got questions from a student perspective, then feel free to get in touch. If you want to ask more about the degrees, then I can put you in touch with the right people if I can't answer it myself. We are hoping that soon as we come out of lockdown, we will start to have open days on campus. We are all looking forward to that. So you can come and see what we do and how we do it in our facilities. But at the same time, if teachers have got questions, if you want help with something or pointing in a direction, in fact, if you've seen anything here today, because one thing I haven't done is told you where I've got all the images from. Many of them are free to use stuff from the internet. For example, Wikipedia Commons. It does have some good images. The thing I would say about Wikipedia is that anyone can edit, so you don't always know if the information is very accurate. The images are great to use, but there's a number of the images I used here that are from papers that either I've been involved with or friends and colleagues have been involved with. And if you've got questions about any of the images or questions about any of the content, I can put you in touch with or put you in the place where I can give you more information. It'd be a total pleasure. But I would like to point out that I do feel for teachers who have to try and cover all of this with everything to do with rivers, with everything to do with climate change. I mean, so as Craig said, how do I try and do it? I try to get this into everything, but I don't have to do rivers. Craig does rivers. I don't have to do all the volcanoes and the earthquakes and I just do tsunamis. The rest of the hazards can be done by Matt. So we're really lucky at university because we have our specialities. But that's good for students as well, because you get to see all of us in these different ways. But it's very hard for teachers to try and cover everything. And I know that sea level can be a tricky one. So if you have got questions about things or further reading or ideas, then please do get in touch. And same with students.
Perfect then. So thank you ever so much all. Again, we're going to take a bit of a break next week. So with it being Easter and whatnot, so there's no seminar, there's no webinar next week. We're back up again in 2 weeks' time with Dr. Mike Kennedy, who's going to be is looking at ecological and the impacts on biodiversity and ecology. So I will see you all in a couple of weeks. Thank you ever so much. And once again, sorry for the slight delay at the start. And thank you ever so much, Jason, for.
Not a problem.
See you all later. Cheers, guys. Thank you.
Bye.